Okay, just checking this is on. Yep, that's fine. So, good afternoon, everyone. Thank you very much for coming to this side event at the UK Pavilion. My name is Leo Hickman. I edit a website called Carbon Brief, where we cover in quite a lot of depth kind of the latest climate science and latest climate policy developments. And this particular side event is focusing on a really, really hot topic and fascinating topic and big area of research amongst climate scientists, the subject of tipping points. And we're going to hear from our excellent panel exactly what we mean by tipping points and some of the different tipping points and why they are an interesting area of research, but a vitally important area of research. And then we're also going to hear about how that research is feeding into some of the policy-making decisions, both here at the COP and also maybe back home in capitals and governments around the world. But this, as you can see from the screen, we're focusing on some of the key tipping points. There are 10 or so big tipping points, which you often hear talked about, but we're focusing particularly on, I think, sort of 3 or so today. But we're going to begin with a sort of an overview presentation to kick things off from Marissa Montoya, who is from the University of Complutense here in Madrid. So why don't we begin now, and I'll hand over to Marissa. And then once we've heard from all our panelists, then we can open it out to Q&A, because I'm sure there's going to be lots of questions. And we've got pretty much an hour to have this discussion. So I'll hand over to Marissa. So I'm going to sit down so I can see.
So I need this. Okay, so good afternoon, everybody. My name is Marissa Montoya, and I actually belong to the Complutense University in Madrid, which is one of the largest universities. Let's see if I can handle this. Okay. So I guess this was part of the presentation that was meant to be explained before. I guess I will go straight ahead to my slides, right? So I think I'm here because I'm involved in a project which is an EU-funded project which is called TIPPIes. There has been a lot of discussion about the name of the project, how you should pronounce it, but we came to an agreement. And this project is about tipping points in the Earth system. It's a EU-funded project. It involves more than 10 countries and from 18 different institutions, and we intend to hire about 30 postdocs. So I'm here on behalf of the coordinators of the project, who are Peter Dept and Nicholas Boers. So to start, I should explain what a tipping point is. And the thing is that, as in many complex systems, the Earth system has large-scale components that exhibit a threshold behavior. And this is what I'm showing in this panel. I'm not sure if I can point to this. Well, apparently not, but... and this means that the system can show a very large and abrupt response to a small perturbation. So here in this axis, we have a tipping element, which is the kind of the type of element we're talking about, of large-scale system. And the threshold behavior is described here. So this means there would be a certain threshold, which is shown here as this row. I thought I would be able to point, but I'm not. So the tipping point would be the level of a control parameter, which in the case of the Earth system would be basically radiative forcing, ultimately in response because of anthropogenic greenhouse emissions, so that below the threshold the system would be in a state, and above the threshold the system would be in a completely different state. So if we perturb slightly the system, it can suffer an abrupt, so a large and rapid transition from one state to the other. And underlying, so at the heart of this behavior is the existence of positive feedbacks that kick in once you get to the threshold and that dominate the system dynamics for a certain period of time. So normally what we think in climate sciences is that tipping over a tipping point involves the transition of the state from a state which is desirable, which is shown there in blue. It's the desirable state, and this would imply essentially it refers to the state basically in which the Earth system has found itself for the last 10,000 years or so, the Holocene. I will talk about that afterwards. To an undesirable state, which means a state in which the system has properties that are not, well, desirable. And this has led to the definition of what we call safe operating spaces, which would be essentially this desirable state. And we think that the system, the Earth system, has processes which have already undergone, let's say, transgressed this safe operating system. And this has to do, I mean, this is the case for climate sciences and for other processes, like, for example, loss of biodiversity. And there are other processes that could be also transgressing their desirable states. Oops, I went too fast there. So the thing is that this way of tipping is a possibility, but there are other possibilities which are maybe more typical of systems like the Earth system, which is what I'm showing here in this case. In this case, we don't have just one tipping point, but we have two tipping points, and there is an area here in between where the system can have several steady states. Two of them would be stable. This would be these points here and these points here. And there would also be unstable states, which would be the ones here. A stable state means that if you perturb the state slightly, it will come back to the initial state. And an unstable state means if you perturb it slightly, it will run away and end in a different state. So in this case, we would have two different tipping points. These are this rho critical prime and the rho crit, and we can move from left to the right from the safe operating space into the undesirable state. And even if we have transgraded the value of the first critical point, which would be like a kind of soft boundary of the safe operating space, we would not tip into the undesirable state. So we still have a bit of margin. We have to transgrade, in that case, the hard boundary to get into the undesirable state, okay? Now, the thing is that once we've done this, it could very well be the case that if we revert the forcing, okay, then we wouldn't come back through the same pathway. And this has to do with the fact that we think that the system has memory, and that has to do with the fact that there are positive feedbacks. So this means that, that there would be some irreversibility in the system, that it could be that when the system passes this threshold, it could stay in the new state, undesirable state, for a very long time scale, compared to typically to the, I mean, longer than the time scales of the lives of humans, if you want. So what are we talking about when we talk about tipping points? This is just a few of the examples that we're tackling in the project. It would be systems related with the cryosphere, Greenland, Antarctica, the permafrost, but also the AMOC, which involves, it's a large-scale system of currents that will be tackled afterwards by one of my colleagues, and also the Amazon and South American monsoon and the Asian monsoon. So all these, there are reasons, physical reasons, why we think all these components of the Earth system could tip eventually due to climate change into a different state. And we could analyze these separately, but the risk, there is also a risk that because these are all part of an Earth system that is interacting with each other, that tipping of one element could induce a cascade of tipping into the other elements. That is something that we need to address with models. So I'm going to talk about one of these. Well, first of all, to talk about the project, the key project objectives are listed here. We want to identify tipping elements and their interactions in data, especially in paleoclimate data and Earth system models. We want to advance the mathematical theory underlying tipping points. We want to develop early warning signals for future tipping events. I'm basically reading what is written there. We want to characterize climate sensitivity and climate response in the presence of tipping points. And we want to define and identify safe operating spaces to avoid tipping events. And finally, something which is very important, we need to bridge the gap between climate science and policy advice. So I will be talking just about one of these tipping elements, which has to do with ice sheets, which is the field where I'm working in right now. So the ice sheets that we have right now in the Earth system are the Greenland ice sheet and the Antarctic ice sheet, as you probably all know. And these ice sheets are important for the climate system or for the Earth system for several reasons. First of all, because they have a large albedo, so they reflect a lot of the incoming solar radiation, which means that they help to cool the planet. And secondly, because they store a large amount of fresh water. So they store 99% of the fresh water that is in the Earth system. So this means they have a great potential to, if they change their mass, if they lose ice, they have a great potential to increase sea level. So these two figures are from satellite data from NASA, and they're showing something that we're observing in the last 14 years or so. This goes on actually from before, but it has been more dramatic in the last decades. And that is that Greenland and Antarctica are both losing mass at different rates. Greenland is losing mass at a rate, it's written up there somewhere, of 280 gigatons per year. This means about 0.8 millimeters per year. And Antarctica is losing mass at a rate of 125 gigatons per year, meaning 0.35 millimeters per year. So we can see, where you see this in red, it's not because Greenland is red or Antarctica is red, it's because it's the area where it's losing mass. So red is losing mass, blue is gaining mass. So essentially you can see that Greenland is losing mass almost everywhere except at the center, and we understand why this is the case. This is mainly a combination, half-half, of surface melting because it's getting warmer, and also increased discharge. And this discharge is triggered by the fact that warmer ocean waters are approaching Greenland, and this causes melting in the outlet glaciers that Greenland has, and produces a lot of discharge. And this has been happening a lot in the past decade. In Antarctica, the situation is a bit different. You can see all this area in red, which is the area that is mainly losing mass. And some areas are also gaining mass, like here or here. This area is also losing mass. But the mass loss in Antarctica is really very, very cold. So there is basically no melting yet, or almost no melting. So the loss of mass is basically due to ice discharge, okay? And this is what I'm going to talk about, essentially, today. So these mass losses have contributed to increased sea level. We can look at it at different time scales. This plot here shows the global mean sea level rise since the 90s, okay? And we see we have a steady, well, not a steady, an accelerated, actually, sea level increase. Right now it's about 3 millimeters per year, but it's accelerating. And both Antarctica and Greenland have contributed a lot to the acceleration that we observe in the last decades. We can put this in a longer perspective, and for that we need reconstructions of past sea levels, and this is what I'm showing in the big panel. Okay, so there you have, basically, I'm zooming out in here. Okay, so you can see that sea levels that we're attaining today might be unprecedented in the last millennia, okay, even taking into account the uncertainty in the last millennia. But what is more appealing or more dramatic is what we see if we look at projections, okay, and you don't need to look very closely into the numbers because these can change depending on the models. But essentially, regardless of the scenario that we follow, okay, in the best scenario, we would be several centimeters above present sea level. In the worst scenario, in year 2100, in the worst scenario, we would be roughly 1 meter above sea level. But regardless of what we do, we will always be we will always have reached a sea level that is unprecedented in the last millennia. Now, the fate of sea level will depend strongly on future emissions. That is what we see there, okay? But it will also depend strongly on whether we cross these tipping points or not. And that is what I want to explain next. So for that, I will concentrate essentially in Antarctica, which is the big elephant in the room, and try to explain what the processes involved are. So Antarctica is special because of certain features, and essentially what I'm showing here in this panel here is the depth of the bedrock, okay, on which Antarctica lies, right? So everything which is blue means bedrock below sea level, okay, and everything which is red means bedrock above sea level. So essentially a large part of Antarctica, mainly most of West Antarctica, which is this sector here, lies on bedrock which is below sea level, okay? So that means that that ice is in very close contact with the ocean. That is something that you can see better on this plot here. So if we draw a section this way, okay, we will see that we have ice which is resting on the bedrock. This bedrock is below sea level, and ice flows outwards, okay? So it forms what we call ice shelves. So there is a line that separates the ice that is grounded, okay, from the ice that is floating, and we call that the grounding line. And this grounding line migrates depending on the conditions, okay? So if the ice gets thicker, it can advance, and this is what happens in cold periods. And if the ice gets thinner, it can retract, and this is what happens in warm periods. And this is actually what we're seeing now. And that is essentially, that is the reason of something that we think is relevant for Antarctica, for West Antarctica today, which is what we call the marine ice sheet instability, okay? And the reason is that we think that if for some reason the ice gets thinner in this area, the grounding line will retreat, and because of the slope that is, we call that retrograde, so inland, if the grounding line retreats backwards, so into the land, we will get a stronger outflow of ice, and that itself will produce, again, a backward retreats of the grounding line. So there we have the positive feedback, which I mentioned in the beginning was so important for these tipping events. So actually, this is what we think. Okay. No, I'm going the other way, sorry. Okay, this is what we think is happening in Antarctica right now in some areas. Let's see, I have a film here. Yeah, that's West Antarctica, okay? And there you have all those glaciers that are draining part of West Antarctica, okay? And all those glaciers we see that they have accelerated in the last decade, okay? And the process is exactly that. It's this retraction of the grounding line, which goes in parallel with the thinning of the glaciers, okay? This is where the grounding line was located for some glaciers. This is where the grounding line has moved to in 2000. I'm not sure if this will start again in 2011. So we think that this, maybe I can play it again. Okay. So those are the glaciers, they're speeding up. The grounding lines are retracting, okay? And as they retract and this is the slope I was mentioning before, okay? And we think this might be an irreversible process in the sense that once it has retracted, that we need a very large forcing to revert the system to its initial state. One thing that is important is that something that we see in these glaciers is that we haven't seen very often the collapse of an ice shelf. Okay, for these glaciers, what is happening is that the ice shelves are actually thinning, and the ice shelves are very important because they buttress the rest of the ice shelf. So one thing that was seen very clearly in year 2002, where we had the collapse of the ice shelf called Larsen B in the Antarctic Peninsula, is that as the ice shelf collapsed and the grounding line retracted, we saw a very fast acceleration of the ice streams. So this is important because ice shelves themselves, they wouldn't contribute much to sea level because they're floating, but they have consequences for the ice that is located inland, because if they collapse, they stop rebuttressing, and then the ice streams can accelerate and they can drain a lot more ice from inland into the ocean. So this means that if there were to be a total collapse of the West Antarctic ice sheet, sea level could rise between 3 and 5 meters. That is the estimate. So this has implications because, as I said before, we focus a lot on what is going to happen until year 2100, but it's also very important to think of the longer time scales. And the way that climate scientists usually talk about this is saying that we are now committing to long-term climate change, in the sense that we are pumping anthropogenic gases into the atmosphere, and these gases have a very long residence time, so they will stay for long in the atmosphere. So as long as they stay in the atmosphere, they will have a contributing effect to warmer temperatures, and this is essentially what we see down here. So that is CO2, or anthropogenic gases, and this is temperature. And as long as temperatures also have stay at high values for very long, they will also have an impact for very long time scales on ice sheets. So ice sheets will be perturbed for very long. So we need to address also what is the long-term fate of ice sheets, which is this one, which is a bit the justification based on well, part of things that I've been explaining of why the Paris climate target was the right target. You have a plot of the evolution of global temperature roughly since year 20,000 ago, so that was the last glacial maximum, into the future and into the scenarios. And you see that in the target of the Paris Agreement, which is about 1.52 degrees, we could already be hitting some of these tipping points, in particular the West Antarctic ice sheet and other tipping points. And other tipping points might be hit at higher temperatures. So 1.5 seems like the right target if we don't want to do dangerous experiments with the Earth system. Okay. Thank you.
Thank you, Marissa. So I'd ask you just to hold your questions until we've heard from all the panelists. But we've just heard, obviously, about the tipping point in Antarctica and relating to ice sheets. But we're now going to hear from Richard Betts from the Met Office in University of Exeter about another crucial and much researched area of tipping points, which is in the Atlantic Ocean, AMOC. So I'll hand over to Richard.
Thank you, Leo. So I'm actually giving this presentation on behalf of some colleagues, Richard Wood and Laura Jackson at the Met Office Hadley Centre and Pete Ashwin at the University of Exeter. And this is again part of the TIPES project that Marissa just talked about. And this is about, as Leo said, the one very well-known potential tipping point in the Earth system, the Atlantic Meridional Overturning Circulation, or AMOC for short, also known as the Thermohalone Circulation, or THC, or the Global Conveyor Belt. And this is part of a giant global ocean movement, which the important part we're focusing on is in the North Atlantic. The orangey red colour is the surface waters. It brings the warmer waters from the tropics to the North Atlantic, and it keeps Western Europe warmer than it should be at that latitude. And there is evidence from climate models and from paleoclimate data that this has two stable states. And it relates in particular to the input of fresh water in the North Atlantic. So this graph here on the left, it's similar to what Marissa showed in one of her earlier slides, but it tipped around. So it relates to strength of the circulation up here in spur drops, so the strength of the flow with the strength of the freshwater input into the North Atlantic, particularly from Greenland, because it depends on the salinity of the ocean water, so how much salt there is in the water. So salty water is denser and it sinks more. So if you have fresher water, you get less of a sinking motion and less of a pull of the ocean current up from the tropical Atlantic. And as I say, there's evidence in the past that this has switched off. So you can see the two stable states here. This is the present day state with strong AMOC strength, which would decline as you increase the freshwater input. It's possible that you could go past the tipping point at a high level of freshwater input to a new stable state of collapsed AMOC, so you don't get this strong northward pull of the ocean waters. And if that was to happen, if the freshwater input were to decline, you would stay on this low trajectory with a low circulation strength, so you could flip to a different state. Now that's thought to be, reassuringly, somewhat unlikely within this century at least, but not impossible. This is the model projections from the CMIP-5, the fifth set of climate models done for the previous IPCC assessment report, showing the strength of the AMOC historically and then projected on into the future. And the dark red is the average of all the models, and then this shows the sort of the spread of outcomes there. So you can see that all the models are projecting a decline in AMOC, but not necessarily a complete shutdown. And in fact, the IPCC special report on oceans and cryosphere suggested that it was very likely to weaken over the 20th century, but very unlikely to completely collapse. Very unlikely is defined as between 90% and 100% certainty. So still perhaps a 10% chance of it shutting down. So it's less likely, but we definitely can't rule it out. And the impacts of that would be quite profound. We would see a large spread cooling across the Northern Hemisphere, particularly in the Northwest Europe region. So the UK, for example, would get very severe cold winters. But parts of the tropics would warm slightly. It would also change global precipitation patterns, a reduction in precipitation in the Indian subcontinent, for example, the Amazon region, also over Western Europe. And although it doesn't show up here, summer rainfall in the UK would also decline as well, which could have widespread impacts. So it would have major impacts if this were to happen. So it seems to be low probability, but high impact. So how can we manage this kind of risk? Well, one example of managing a low probability, high impact risk is protecting your house against fire. You don't know the chances of your house burning down, but most people will take steps to deal with it. You might put a smoke alarm in, an early warning system, which does two things. It gives you time to perhaps put the fire out if it's started, if you can get in quickly, that's urgent mitigation, or if it's out of control, to evacuate the buildings, that's adaptation to that change. Or you can, in advance of that, develop safe practices. Just manage your property so there's less fire risk by keeping the electrics in good order, for example. And most of the negotiations here are about that second part, about keeping the climate within this safe operating space. I'm going to talk about the other part, the early warning system, in the next couple of slides. So this is the work that Pete and Laura and Richard Wood, and in a paper published by Al-Kahyon in Proceedings of the Royal Society this year, which is it's a theoretical model, which is a model which has been shown to reproduce the more complex ocean atmosphere general circulation models, and it's looking at the potential to use ocean salinity, so the saltiness of the ocean, in different regions, the polar region and the tropical region, as an early warning system. So can you see changes in that before you actually see the slowing down of the circulation itself? So the key point is we're looking at the subpolar salinity, so in the North Atlantic here, and the subtropical salinity up here. So this is very salty water in both regions up here, and fresher water in both regions down here. And there's these three equilibrium states. The red one is where we are at the moment, the strong AMOC circulation. The blue one is the collapsed AMOC state, and this green one is an unstable equilibrium where it doesn't really stay there. And each of these lines is showing a trajectory of changes in the relative salinity of the two regions of the Atlantic. And the point is, if you look at how the salinity is changing over time, if it's tracking in a certain direction, if you see an anti-clockwise track of the salinity, then all these anti-clockwise tracks will eventually lead to a collapsed AMOC. So the idea here is that if we see salinity changing in this particular way to follow this anti-clockwise trajectory, then that's an early warning that the AMOC may be shutting down soon. Thank you. So that's the early warning concept. Another thing to do with that, if we were to see the AMOC starting to shut down, could we do anything about that? Could we, if we were able to mitigate climate urgently, would that actually reverse the shutdown of the circulation? So we've done some climate model experiments with this. So this is using the HADGEM3 climate model, the Met Office Hadley Centre climate model, and it's doing what's called a hosing experiment, where you put extra fresh water into the North Atlantic and you keep that going to deliberately shut down the circulation and then see what happens if it comes back. And the black line is the present day state, or the pre-industrial state. The grey line is what happens if you give an input of fresh water of 0.2 sverdrops, which is about double the maximum we'd expect in the 21st century from Greenland. And if you keep that going, then you do shut down the circulation. If you reverse that after 50 years, then the circulation stays shut off in the red line. If you reverse it after 40 years, it does actually recover, and 30 years and 20 years. So if you were to shut down, if you were to reverse this input of fresh water somehow, then you could actually recover from the shutdown AMOC state if you could do it in time. That's the big if, though. We don't know how this would be possible, but if you could, then you could go back beyond this tipping point. So to conclude then, it may be possible to manage the risk of AMOC thresholds by developing this early warning system based on salinity. This is still very much an early research stage, though, so we need to look at it with more comprehensive models and more realistic scenarios. It's all very theoretical, and there's key knowledge gaps on the detection time, how long we'd need to actually detect this, and the adaptation time, how much warning of a collapse we'd actually get, and the resilience time, how, if we overshoot, how long we'd have to draw back. But I think this is an important area of research to help manage this low probability but high impact scenario. I'll finish there. Thank you.
Thank you, Richard. So moving on, we're now going to hear from Andy Wiltshire from the Met Office and University of Exeter on another tipping point, which is often the much talked about permafrost. So I'll hand over to Andy.
Thank you very much. Yes, so I'm going to be talking about terrestrial ecosystem tipping points. I'm going to be talking a bit about forest, but also about permafrost. And really what I'm want to do is I want to put this into the context of carbon budgets as well. So what does this mean about how much carbon we can emit in the future if we're to meet any of those targets? Okay, but first of all, it's important to note that terrestrial ecosystems are both massive stores of carbon in the present day, whether that be in the permafrost or be in forests, but they're also potential sinks for the future as well. The ecosystems at the moment, the land and ocean combined take up roughly half of all the emissions that are put into the atmosphere. So they're very important. Okay, so what I want to do here now is just talk a little bit about carbon budgets, and that's what this plot shows here. So what it does is relates across the x-axis here the total cumulative fossil fuel emissions of carbon against the warming that you would get from that. And what you can do, hopefully this works, you can then use this to create your targets. In this case, I've just highlighted the 1.5 warming, and you can relate the amount of warming you've got left, you hit that, okay, until the carbon that you can emit to achieve that. And that comes out at 580 gigatons of CO2 from the SR 1.5 report. Okay. Now, as you may have heard from some other events here, these models, these are based on the Earth system models, these kind of relationship, but there are feedbacks and processes that aren't represented. Now that can act to both increase the available budget, regardless if ecosystems take up more carbon in the future, or if we go over some tipping points, then they could actually look to reduce that budget. Now the part of the question is about what timescale that occurs upon. So this slide here now shows, this looks at tropical and boreal forests. So this is both the carbon stored in soils and also in vegetation. And it looks then at what happens once you stabilize climate at 2 degrees, 3 degrees and 5 degrees, what is the potential change in those ecosystem stores of carbon? And the banding here shows the uncertainty. But what I wanted you to highlight here really is that the fact, so that banding uncertainty there both spans, cost is 0. Okay, and that reflects some of the uncertainty we have. And particularly if we look at the tropics, you can see that can go quite negative, and that reflects the possibility and the risk of ecosystem collapse. So the Amazon dieback being an example of that, and we feel that the models show the risk of that increases with the actual temperature that you hit and stabilize that. So they could be contributing significant amounts of additional carbon to the system. Conversely to that, we also expect ecosystems to take up more carbon, particularly the models show boreal forests moving further north with warming and potentially being a greater carbon sink. So you can also see there are positive numbers here. But the distinction I want to draw there is that the movement of the tree line and forests, that's a slow process that will happen over potentially hundreds of years. But some of these fast effects may be related to a forest dieback, could be quite rapid, and actually you might see those kind of things happening by the towards the end of, or maybe early next century, particularly if we hit some of these really, really high temperatures. So it's a kind of risk kind of basis that I'm trying to suggest here, that by stabilizing at lower temperatures, you actually reduce the risk of some of these potential feedbacks. Okay, and now this just shows what happens when you include fire. So this is the role of wildfires, and we think wildfire might potentially drastically increase the chances of these tipping points happening and getting significant additional contributions. Okay. I said I'll also talk about permafrost. So we don't necessarily see permafrost acting as a tipping point, but what we do see in the results and modelling so far is as you go to warmer temperatures, which is plotted here across the x-axis, you see it producing potentially a larger negative contribution to that carbon budget. So here we see, I don't know, as an example, you're looking at sort of 3 degrees. The medium estimate there is around 200 gigatons of CO2 negative. So that's approximately a third of the budget we've got remaining to the 1.5. So that means if these things occur, that means we'd have to reduce more in the present day to avoid these happening. Okay. The other piece of thing I want to say with that, so the first thing was to say there is the risks increase the higher the global mean temperatures that we actually hit. But then I also wanted to point out that these aren't always, it's completely dependent on what the actual temperature you achieve is. The pathway to how you get there does matter. And that's what's plotted on this plot. Okay, and across here, the x-axis, that doesn't work, does it? Shows the degree of temperature overshoot. So this is down here, you've got 0, that's if we hit the 1.5 target, okay, without overshooting. Now this one here shows if we don't include negative emissions in the scenarios, and what that means is that actually emissions tend to peak later, okay, and that means that actually permafrost we expect to give you a slightly bigger contribution, so in which case you have to reduce even more. And the more you overshoot, so this is a ½ degree overshoot, a 1 degree and a 1.5, potentially you're getting an additional contribution of up to 250 gigatons there. So potentially, if you overshoot, this makes the challenge, okay, of achieving these targets much harder. So you can't necessarily trade 1 unit of fossil fuel emission in the present day for a negative emission in the future, if that means you overshoot your target. Okay. So, just to summarise really, the 2 main points I kind of wanted to show there was that the higher the temperatures we achieve, the greater the risk we see of some of these negative effects, potentially tipping points related to forests responding to climate change and drying, but also we also see this kind of effect in the permafrost as a stronger contribution to the budget, if not actually a tipping point, but it is largely and pragmatically it could actually be irreversible. And finally, this pathway by which we actually achieve the targets does actually matter as well. So overshoot will have implications as well, and will mean reductions will have to be larger, most likely. All right, I'll finish there. Thank you.
Thank you, Andy. So we've just heard 3, I would say, pretty sobering presentations, but there's another important part of this, which is how does this information get fed to policymakers, which is obviously poignant for where we are right now. So we're now going to hear from Siobhan Browne, who's a senior science lead at the UK government's Department of Business, Energy and Industrial Strategy, to hear about how, I guess, you translate all of this latest science and research into the in tray of politicians and advisors and other civil servants. Okay.
Thank you, Leo. And it's great to be here today, and it's actually really interesting to hear some of these talks from these scientists that we have here. I think, as Leo mentioned, I sit in a science team in the Department for Business, Energy and Industrial Strategy. One of the key things that the UK government is really proud of is the fact that we actually use the best available science to inform our policy and decision making. As most of you will have heard, particularly if you've been at UK events this week, the UK has set a net zero target by 2050. And this target's been based on the best available science that we have, particularly the IPCC report of 2018, which was the 1.5 degree special report, which many of you will be aware of. This target has been set by the UK government. The 2050 net zero target has been set by the UK government in order to be consistent with the Paris Agreement. And as far as possible, this approach was taken to minimise the risk of climate change, and hopefully, as we've heard from the presentations, from tipping points as well. In terms of what the UK government has kind of been thinking about with tipping points, the UK Climate Change Risk Assessment, which was published in 2017, included high-end climate change scenarios. These included extreme climate change scenarios on the margins or outside of the 10th to 90th percentile range of the 2009 UK climate change projections, which have recently been updated to UK Climate Change Projections 2018. So these high-end scenarios that we use from 2009 cover different climate hazards, including heat waves, extreme rainfall and droughts, just being 3 examples, but they don't explicitly account for physical tipping points being crossed. In terms of physical tipping points, there are some examples in the UK where we have factored these into adaptation decision-making to some extent. One such example is the Thames Estuary Barrier, the plans for 2100 for that barrier. Project decisions in this example took the barrier height, took into account estimates of whether we're likely to see catastrophic sea level rise this century. Generally though, and I think this is a key point for policymakers, one of the big uncertainties of physical tipping points and their magnitude means that many decision makers prefer not to additionally invest in protecting infrastructure for events that are considered, perhaps wrongly as we've heard today, events that are considered very unlikely. As I mentioned, the Thames Barrier is a kind of exceptional example of this, but it is a challenge in terms of uncertainty and demonstrating this for decision makers. It's very hard to get those points across. I think it's also important to note, which actually changes tack slightly from the presentations we've heard today, that it's not just physical tipping points that governments need to be aware of, but socio-economic tipping points will be a key point as we go forward as well. And these won't just necessarily happen because of these big physical tipping points that we've heard about today, but potentially also due to kind of ongoing climate change impacts that aren't seen as these big tipping points, but generally occurring, such as continued drought, which might lead to bigger social changes. And as I say, these social and economic tipping points are just as relevant for decision making, potentially if not more so, but are even less well understood. One of the other things I was asked to think about for talking here today is what the knowledge gaps are and the information that would be required for tipping points to kind of feature in mainstream decision making for governments. I think there are 3 key things. One thing I've mentioned is the social tipping points just now. Another one is the economics around tipping points. But in terms of the physical tipping points, which we've heard about today, and actually one of the things I'm going to mention, one of our speakers has already talked about, a key knowledge gap is the effective overshoot, particularly in relation to ecological tipping points, which Andy mentioned just now. We need to improve our understanding around the size and length of an overshoot and how that relates to the irreversibility of these changes. And that's a key piece of information that we need to know about to inform mitigation choices. So I think just to sum up, it's really challenging to kind of get some of this science where it's got high uncertainties across the decision makers, particularly where this will have a large cost implication. We do, as I say, the UK, we do kind of aim to keep our decisions based on the best available science, but with some of these uncertainties, it can be very challenging. But it's great to hear from the scientists today about where some of these issues lie.
So we've got sort of 15 minutes or so, got a bit of time for some questions. We've got a great turnout, so I'm keen to move the questions over to you guys as soon as we can. But I've got one question, just before, I've got many questions, but one question in particular, which is maybe spinning off from what Siobhan just says. All of those presentations are quite, from my perspective, alarming, sobering, etc. But they're talking about quite far off timescales in terms of policymakers who are in 5-year election cycles, etc. In terms of telling today's policymakers what they need to really, really be concerned about, other than just saying all of them, is there a particular tipping point that keeps you awake at night? Maybe Marissa, I'll start with you. If you hand the mic along, yeah.
Yeah, well, I agree with what you said about politicians, and the timescale of politicians is not quite the timescale of ice sheets, but I think we are aware now that what we're doing now is going to have an impact in the long term. And considering your question, I might be biased, but for me it's yes, the West Antarctic ice sheet is the tipping point that keeps me awake at night. Because I think There are several reasons for that. We're seeing that it's changing. We see that it changes. The attribution is not easy to climate change is not easy, but it's changing in the direction it would change if it would be responding to climate change. For all that we know, this change is going to be irreversible. If it's not irreversible, it will be a big surprise. And we know it has happened in the past. We know that the Antarctic ice sheet, in particular the West Antarctic, has changed a lot in the past in response to climate change. So yes, that's a tipping point that keeps me awake at night.
Okay.
Maybe
Richard?
So we may all just sort of answer the ones that we spoke about ourselves. So when I was being briefed on my presentation by Richard Wood, who prepared the slides, I asked him kind of that question about, well, you said about these impacts being, and the tipping points being a long way in the future. But I think the AMOC, although it's unlikely, isn't necessarily a long way in the future. It could happen literally at any time. It's unlikely, but it still theoretically could happen almost at any time. Although perhaps the reassuring side is that some of the research suggests that it might be reversible if we could act quickly enough or deal with it. But I think we shouldn't be complacent that they are all a long way in the future.
Okay. Andy?
I might give a slightly different answer, actually. So we heard Rich talking about the need for early warning. And I guess the thing that perhaps concerns me is that there are early warnings, but it might be that we don't actually recognise them as such, okay, and therefore we miss the signals, and I think that may be applied. Maybe we talk about the sort of West Antarctica itself, maybe also when we're looking at things like the Amazon forest as well.
So is it, just picking up on that, is your fear perhaps that the West Antarctic ice sheet, we may have already actually passed the tipping point 15 years ago, but we don't actually yet know because so it may actually be too late for something. We may be on that journey of irreversibility.
Yes, I mean, there are studies saying that we have probably already passed the crossing point, not maybe 15 years ago, but in the last decade or so or a bit more, we might have already passed the tipping points for some of these glaciers in the Antarctic ice sheet, in the West Antarctic ice sheet.
We've had many headlines around the world recently with that Tim Lenton paper
Yes.
that was in, I think, Nature or Science?
Nature.
Just a couple of weeks ago. And we've heard from, it's topical today, Greta Thunberg saying when she reads the science and, tries to absorb it, she's concerned that these tipping points are not being included in a lot of the, sort of, say, IPCC modelling. And that there's a date from her perspective and other people saying maybe we're not actually absorbing some of these, sort of, okay, they may be low risk and distant, but actually they would have such a high impact that they're not being included.
Yeah, I mean, what I would say is it's not that the tipping points are not included. It's that we're having difficulties to simulate, maybe we can all comment on that, abrupt climate changes with models. We know that in the past, we see from the paleo record that there were abrupt climate changes and models are having difficulties to reproduce them. So there has been a lot of discussion that goes in the sense of saying models are maybe too stable and we might be a bit too conservative right now in terms of interpretation of model results. Maybe others have other perspectives on that, but that is what I would say.
I was just curious to get Siobhan's thoughts on, so you've got a busy minister who doesn't have much time, you've got 5 minutes to get their attention. So, and they hear about tipping points. What single tipping point do you try and brief them about or try and update them on?
Yeah, that's a challenging question, I think. And I think for us, it's not about picking out kind of necessarily one particular issue. I mean, I think for us, our ministers often like to try and speak to the scientists as well, and we've got kind of ministers out here as well. And I think for us, it's about getting across those points that actually these things are further in the future, but it doesn't mean that we should think about them now. So rather than necessarily picking out kind of one key tipping point that we might talk about, I think for us it's exactly that timescale point of saying, although these things might happen in the future, there's something that we need to think about now and kind of really taking this kind of key science point to explain what that could mean if we don't address it at this point.
Okay, thank you. So we're pretty short on time. We've got sort of 5-10 minutes maybe max. So I'd really beg, when the mic goes round, we just have very crisp, succinct questions, not comments, please. I'll just have to be quite strict on that. So we've got a hand raised here. Thank you.
Hello, my name is Gabriel. Thank you very much for this very relevant debate on tipping points. My question would be, we talked about tipping points with a positive feedback mechanism. Are there any known tipping points with a negative feedback mechanism as well?
Okay. Yeah, good question, mate. Richard? Yeah?
So yes, one example would be in West Africa, the Green Sahara concept. It is known that in the southern Sahel area, that seems to have two stable states, and in the mid-Holocene it was greener and wetter. It's possible that that could actually green up under climate change, and that would be a negative feedback, although most of them, as you say, are positive feedbacks, like self-reinforcing, making the impact larger.
Okay, another question? Got one down here. Thank you.
On the issue of model stability and thinking about the point that Andy made about fire, which the introduction of fire radically changed the results, is this implying that we shouldn't really actually trust these models that much?
Andy?
No, I don't think it's the case we shouldn't trust them, but I think there are certain things that we recognise aren't included, and I think as a climate modelling community, we're working to address those kind of things, and so we can trust them, I think, but we do need to take that into account and think about what's included, what isn't included, okay, and have that sort of general message around there that it's not just one answer. If you sort of mean, you do need to think broader than that.
Okay, thank you. Got a question here.
Thank you. Relative risks of other tipping points, oxygenation, acidification, jellyfish burgers, anybody?
Is that a question?
Well, it's just saying are there not an awful lot of other tipping points that maybe we're not giving adequate...
Oh, for sure. But this presentation was obviously limited to 3 very key ones, but I agree. Maybe I'll just do a little plug. So Carbon Brief is preparing a series of articles in January looking at 10 key tipping points. So if you keep an eye out on our website in January, we'll be publishing a whole week's worth of articles dedicated to tipping points. Maybe not jellyfish burgers, but... Okay, got a question here?
Thank you. My name's Clara Gallagher. I work at the Environmental Protection Agency of Liberia. So we heard quite a bit about the kind of analysis that is there in terms of policy making after you've taken the science for the UK in terms of base, and then it kind of feels mostly European. Is there any good resources for policy maker support in like West Africa and developing countries in general to look for?
I guess the obvious one would be the IPCC, where there was some coverage of or discussion of tipping points in the special report on oceans and cryosphere, and I would imagine there'll be more in the 6th assessment report, which is currently being written at the moment. Incidentally, please act as a reviewer of that. The impacts adaptation report is out for review at the moment. That kind of question could be put in. Say we need more on that. That's the first answer. But I guess also more generally, it's important for research projects to think about how to have that pull through to policymaker and decision support. So we should all keep bearing that in mind, I think. Yeah.
Okay, we've got a question here. Yep. Oh, just behind you, sorry. Yeah.
Hello, and thank you for those presentations. My name is Appy, and I'm the Icelandic youth delegate. And I originally graduated biologist. Obviously, the Gulf Stream is really important for Iceland. We probably wouldn't be living there without it. And I've often heard that if whether the Gulf Stream will move or not depends on how fast the Antarctic versus the Arctic melts. And that if the Antarctic melts faster than the Greenland, then it will move, but maybe not. So I'm not completely sure about this, but my question is, so if we have maybe already reached the tipping point in Antarctica, doesn't that mean that it's more likely that the Gulf Stream and other streams in the Atlantic might reach their tipping point really soon, and maybe an irreversible one if the Antarctic tipping point is irreversible.
So is that a question about tipping points actually merging together?
Yes,
Yeah.
yes, about those kind of two, what your talks were about those two tipping point merging, kind of.
Marissa?
Okay. So, I mean, I'm not sure if I completely got the question. So, if you said if Antarctica is already tipping,
Yes.
would that have?
Would that mean that? So wouldn't that mean that?
Would that compensate for tipping elsewhere? Is that what you mean?
Yes, kind of, or like, yeah.
I mean, it could be, but I think that is very speculative. So, depending on where you put the fresh water in models, you can have a very different response. And you would have a different response depending on the background climate that you use in the model. But I would say probably in the present climate, no matter where you put the fresh water, if you put it at a state that is has a strong AMOC as we have right now, that eventually would cause a weakening of the AMOC. That depends very much on the background state. So I think both would be bad right now.
Yeah, of course.
It could be different if you have a large freshwater input in the North Atlantic. I have to rush, and then the AMOC shuts down, and then you force from Antarctica. You could have different effects, but yeah.
Thank you.
I'm being told right at the back we're basically run out of time. If we have one very quick question, we can probably squeeze it in here. Yeah, and just very quick response. Thank you.
Hi, I'm a PhD student at UC Berkeley, and kind of the topic of uncertainty, like our science models, like from projecting to the future, there's often uncertainty in different ranges. My question was regarding uncertainty in talking with politicians. How have you found that it hasn't been challenging, or how have you managed that topic now, especially in an age where there's a lot of climate skeptics as well?
Yeah, and I think that's a really key question. And I think for us, I think the UK is a good example. I appreciate there are other countries as well that considering these factors. It is an area that can be challenging, and uncertainty, I think, is one of the areas which is hardest to communicate. But I think the evidence that we're getting, particularly from the IPCC, as we've spoken about, is really key. And although it highlights the uncertainties, I think it's quite unequivocal now what the science is saying, and we can share that with ministers, and certainly our ministers are really listening to that advice.
Okay, thank you. Just before I urge you to thank our panelists, just to say, I think you're saying if there's any slides that anyone wants to see, then maybe stay behind and swap cards, etc. I'm sure we can arrange that. But just to say thank you very much for the presentations and the contributions. Thank you. Oh, and you're going to be outside? Okay, yeah. So we're going to come outside if everyone's got any further questions.